All right, so for engineering physics, we should go into a little bit more notation than we have thus far. And what I mean by that is that you've seen in your assignments this week some notation that we haven't explicitly gone into in some of the other mini lectures. Now, the reading sorts all this out for you, but I wanted to say a few words about it. And maybe the first thing to do is to define our position vector. This time, instead of in 1D, where it's just a position, positive or negative, on a number line, so something akin to this. Moment. Right. If this is plus and this is minus and this is the origin, then a position on here would just be, say, like right there, and it would be positive, positive 2 meters or something like that. So positions in one dimension are really simple, all right? But let me just chop this out of here since we don't really want to care about 1D stuff right now. When you start getting into 2 dimensions, well, then your position vector, usually abbreviated as R, is either denoted this way, for 2D, or, put a little dot here, okay, you can add a third dimension. It looks much the same. And let me just spell out a few things here, okay? Identify a few things. Okay, so this is our position vector, and this version is for 3D. And then we've got these coefficients, okay, which would tell us, for instance, what the x, y, and z coordinates were for some vector in a plane. So let's see how my 3D drawing is these days. So we have this guy, and this guy, and this guy. And as far as labeling those things, you generally want to have sort of a right-handed coordinate system. So I think that's, well, we'll get something that looks like this, okay? And if you have a vector in that plane, let me grab a different color. So something like this. And we drop down just to make it clear sort of that it's over and above over here, okay? So that would be your R, potentially as a function of time, okay? If this thing, some object is moving around, and this would represent the position of that object at a particular time. And so the x, y, and z parts of this vector, okay, would be, for instance, let me grab another color. The x portion would be dot, 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 like that, dot, 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 for y, and dot, 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 for z, right? So this would be the x and y and z portions. Now, those things are just magnitudes. So these right here, I would tell you magnitudes. Okay, so how many meters, right, in terms of standard units. And the directions of those things are given by a combination of two things. One, given by these, the I and J and K with the little hats on them, and whether or not you have a positive or a negative sign out in front of these coefficients on the x and y and z. Right, that would just tell you in what direction on that axis you should go. Now, these I, J, K with little hats on them, those are what are called unit vectors. And they're called unit vectors because they are vectors of unit length. So unit length meaning length of 1. And so they don't change the magnitude of these coefficients, these x's and y's and z's. They just indicate direction. So when you see, for example, a j hat on the end of some number, so if you were given, for example, r1 as a function of time is 5t j hat, right? That would tell you that the position of this object is linearly increasing in the positive y direction times 5. So like every second that goes by, it would cover 5 meters if we're doing this in standard units, and we generally will, okay? And if you change that unit vector to an I or K, then that would indicate the X and Z directions, respectively, all right? So what they would look like over here, let me grab maybe a different color, purple, nice. What they look like over here would be like, in the y direction, this would be the unit vector j, in the x direction, that would be the unit vector I, and in the z direction, that would be the unit vector k, all right? Go back to red. So this would be one example. Now, once you've defined your position vector, well, then defining things like displacement and velocity and acceleration, well, that all looks pretty familiar from our definitions of those quantities in one dimension, right? So if, for instance, we wanted to define a displacement, well, that would be delta r as a function of time. And that would be some final r, or I'll call it r2, okay, as a function of time, minus r1 as a function of time, right? Again, just a difference in position. And if you wanted to define velocity, well, if you wanted to define instantaneous velocity, well, you take the derivative, the time derivative of the position vector. That's going to be equal to this. And that in turn is equal to ddt of x versus as a function of time, and of ddt of y as a function of time, and also ddt of the z position as a function of time. Okay. So yes, you can separate out the derivatives in this way. The unit vectors you can just kind of factor out. You're just taking effectively the derivative of these functions, as they might be constants, or they might be, like this one was, just, single power of t, or might be something more complicated, but that's the basic idea. And what this boils down to is that you've got the x component of the velocity, you've got the y component of the velocity. These are all functions of time, of course, potentially, and the z component of velocity, all right? So this would be the definition of instantaneous velocity. Of course, average velocity would just be a displacement, right? Or I guess I shouldn't do that. That seems like I'm drawing an equivalence, doesn't it? So if we wanted to find average velocity as a function of time, then what's that in 1D terms? Well, it's delta x over delta t. So here that would be delta r over delta t. And that would just look like, written out, something like that, right? T2 minus T1, I suppose, in the denominator, if you wanted to be a little more accurate about it, okay? And then so on and so forth, right? If you wanted to figure out what the acceleration was, for instance, well, then you would take the time derivative of each of these pieces of our velocity graph, because the instantaneous acceleration as a function of time is equal to dv dt. You can write it that way. And so that would look very much like this kind of procedure, except all of these little pieces, right, would be the x and y and z components of the velocity, and you'd be taking time derivatives of all of those things, right? So thus the definition, more generally speaking, for these basic quantities of physics in 2 or 3 dimensions. And that's just to familiarize you with that notation. Also, if you're working on the assignment and you see something like that and it's not looking familiar and the reading's not making much sense, then maybe this can orient you a little bit. And we'll say a few more things about this. Maybe I'll solve out a problem in a separate video, but just to get you used to the idea of it. And I'll see you in the next one.